There we go. All right. Shit.
All right.
Hello.
Hello, everyone.
Hello, everyone here. Hello, everyone world. We should hopefully have 8 other meetup groups streaming us at the moment. I'm going to keep an eye on my phone. I'm not being rude. I'm just checking to make sure people can hear us. So thank you very much, everyone that's here and everyone that's joining us online and at the other events. This is kind of a mad idea that Carol came to me with back in end of November, I think.
You came back to me, actually. So
I know.
yeah.
We both had a mad idea independently and agreed to try and set this tour up with some of the NDC speakers. So some of the Microsoft MVPs and the Microsoft staff over at NDC. This week, we wanted to see if we could send them out to some of the community meetup groups, get everyone together for these in-person events and hopefully the live stream as well.
And we collected actually a bunch of local speakers as well. They are not here at this event, but in the streaming events, like we have actually Microsoft employees, even local MVPs, or just community members. So, yeah.
If you're going to tweet about the event or talk about the event online, can you please use hashtag .NET Tour UK? That's the sort of Twitter tag that we're using on social media as well, so we can kind of keep the community, the wider community, involved in what's happening at all of these events.
And I apologize for the UK over there. Steve didn't stop me. Apparently, it's wrong. It is because this is more England. So sorry. The differences are still a little bit lost to me. So next time we're gonna get better at naming. Naming is hard. We all know that, right?
We'll either improve the naming or we will get Scotland and Wales involved in the events as well. But it's quite far from NDC to some of those locations. So we have got, we had 9 events signed up. We had one had to drop out, but we've got still 8 events running, kind of around the south of England, as we should have probably named this. So we've got, obviously this group here, we've got the London meetup group are coming together at the NDC venue this evening. We've got .NET Oxford, we have Reading, we have .NET Southwest, Milton Keynes, and then we had DevOps Knots and the Birmingham Xamarin and .NET user group join us as well. So we've got a nice scattering of events.
A special shout out actually to the Canary Wharf. Like they didn't want to cancel, but unfortunately there are some personal reasons and stuff that happened. So hopefully everything is all right over there and people can join us at least online.
All right. So, and across those locations, we have 16 fantastic speakers. I hope I actually did find everyone. I tried to find the best LinkedIn photographs of everyone I could. There's some rather strange faces and things on the Twitter handles, but these are best I could get. So we've got 16 experts, as I say, local speakers, MVPs, Microsoft staff, kind of joining us. Obviously here we have Irina and Carol joining us this evening in Brighton, and hopefully everyone is happy with the quality of speakers we've been able to send your way, kind of scattergunning out from NDC.
Is that a 10-second delay?
There's a delay with a delay with that as well, apparently. And hopefully we have about 600 plus attendees, according to the sign-ups on Meetup across the various locations, and potentially millions across the world are signed in at the moment. We will check the YouTube stats later to see if we've broken any records, but there's a really good turnout, given that some of this was a bit late notice in terms of confirming which locations, which speakers could come along. It's really good that the community have been able to come together so quickly to kind of join in these events, and certainly here in Brighton we are full tonight, so it's a really good sign and show of the community coming out for the event here.
I have to actually say on that it's actually great to see here in UK, I mean in England, south of England, so many kind of groups so nearby. That's not something that I've seen anywhere else in Europe. Like usually have to drive at least 2 hours. Over here, like in 1 hour drive, like even train. It's actually a pretty strong .NET community, so awesome. And 10 seconds go.
Woo! Might as well walk to the mouse, man. Oh, there we go.
You're gonna have some fun, Irina.
Oh yeah.
I might give you the keyboard. And also, we just wanted to say thank you to NDC as well. They've obviously sort of been involved and given the venue at the QE2 Centre that's going to be the venue for NDC for the rest of the week to the meetup group to run there. So thank you for them, and thank you for all the speakers that have come from NDC as well to join us. Perfect.
And just
no.
There we go. Details. That works. Awesome.
Yep.
Just a few words about .NET Foundation. I'm just curious, I can't ask online, but who here knows what .NET Foundation is? Right, 10 people, maybe less than that. All right, so let me talk about it real briefly. .NET Foundation is a foundation, surprise, surprise. It was created by Microsoft, but it's not only Microsoft. Many people think like, .NET Foundation has to be only Microsoft. It's backed by actually 10 companies. I tried in my cheat sheet to kind of remember them. I know there's Google, there's Unity, JetBrains, and a few more. Red Hat definitely, Telerik, and I forgot probably 3-4. There's 10 of them. AWS actually joined, I think, in November or something like that. So behind the .NET Foundation, it's really not just Microsoft. It's just technical steering committee, including like corporate sponsorship and that stuff. It's like multi companies, companies that are invested in .NET, including big players in cloud and everything. The interesting thing is that why would you care as .NET developers? You can join. There's some voluntary fee that you can pay for, whatnot. But the key thing is that if you join the .NET Foundation, if you care about .NET and how it works in the community, you can then vote the board. We have I think 7 board members. Only one of them is in Microsoft, actually, as of 1st of January too, because Oren joined Microsoft. But he was voted by community. Actually, community voted for the kind of board members. And as a regular member, which for example I am a regular member as well. On my kind of side partners, as kind of me being part of Microsoft, you can kind of help with various activities, like either if you're if you like to kind of do meetups and things. You can kind of look into diversity. There's kind of another thing. There's thing how to kind of help teaching .NET at schools to kind of younger kids and that type of stuff. Lots of interesting things, marketing, other things. Go check it out. .NETfoundation.org. Very hard to remember URL. Yeah. So yeah. Perfect. All right.
So I think that's pretty much it for the intro that we're going to do for all of the other meetups. So everyone's going to be kicking off their events. We're going to continue live streaming hopefully here. So if people are watching from home, we'll have our two sessions hopefully live streamed for the rest of the evening, barring any technical hitches or delays on my clicker. So a big thank you again to all of the groups that have come together to do this, all of the attendees, all of the speakers, and particularly all of the organisers that have put these meetups together. It's a lot of effort to pull all these bits together, particularly at the short notice that we were able to give some people. So it's a big thank you, and hopefully everyone enjoys their evening.
Yeah. Thank you. Have fun wherever you are.
All right. Okay, I'll introduce Irina, Microsoft's MVP from Romania, and I think your session's on HTTP, if I'm correct, if I can remember.
Yep.
I'll give you this. If it's laggy, just use the arrow.
If it's under that, maybe you should open the door.
These wireless technologies.
No.
Oh no, it's good for you.
Now we broke it.
Nope.
Oh, actually, I need to give you the right deck, don't I? It's all high tech over here. That one.
That one.
That one.
Okay. Nice to meet you. I run a user group at home, but never ever was the attendance so big as this night. And a fun fact, we kind of have the same number of members as you do here. So I'm very excited that you're here tonight, listening to me. So tonight I'm gonna try to make you forget about HTTP when it comes to microservice communication, especially. Because I learned the hard way. That is not the way to do it. So, about me, I'm in Romania, in Iași, the second largest city of Romania. I teach .NET. I teach as a, let's call it a professional reconversion school for people that try to get into programming. So twice a year, 5 months, I teach about .NET and C# and the world around it. And I'm very accomplished as a teacher when a student of mine hires. So moving on, we cannot talk about microservices and the way of communication without talking about monoliths. So we need to pass through that. We're going to talk about HTTP calls, sync or AC, RPC, and the big messaging infrastructure or world. So, monoliths. Who ever worked with monoliths? Who loved them? I must admit, because those monoliths were very self-contained. So having a single code base basically made our life very easy. If you ever needed a dependency or to instantiate a class or something, you had it in there. You needed not to worry about whatever repository that is on GitHub somewhere that you need to pull down and run locally to make things work. So everything was in there. Why do I say that it's an easy life for developers? Well, I remember sometimes when I opened the solution, pushed the shortcuts for build, and I had to step out and take a coffee because the solution was so big that it took a lot of time to compile it and build. So that's why my life was easy back then. But it has some drawbacks in terms of technology stack. Pretty much, if you had it in .NET, it was .NET. If you had it in Java, it was Java, and pretty much that's it. We're not talking about the JavaScript and front-end things combined with server-side. But in terms of deploys, it was all or nothing. You didn't get partial deployments. It either worked or not. At least you knew a thing. It won't work, and that's it. So downtimes. Depending on the solution size, downtimes were big in certain situations. And continuous delivery, what was that? You kind of couldn't do it. And it was hard to test. For example, I had pretty much an army of testers that did regression testing, smoke testing, and pretty much every kind of ever invented testing every time we needed to deploy the application. So it was very hard for them and hard for us that we needed to stay over hours sometimes to be there and fix if there was a problem. Okay, monoliths. How do we scale that? How you used to do that?
Up and down.
Up and down. But especially like adding
Oh,
a
Yeah.
bigger machine, right? And when we're talking about costs, a bigger machine, a double in size machine didn't cost double in money. It could be, I don't know, 4 times or 5 times the money. So we call that scaling up. So bigger machine to serve your needs. Money, ours, not. But our company's money, our clients' money, so we needed to take care of that. I'm not saying that either type of scaling couldn't be made. It could, on the horizontal line. But then we said, okay, this big ball, we split it. We do microservices now. But kind of each and every micro, we call it micro, but actually was a service if you analyze it well. Every single unit of these tends to grow. You have the tendency of growing this micro into services and then become monoliths, and then you're back to square one. So what is a microservice? Is that thing that is not a monolith. Because in real life, pretty much this is it. Not a monolith, we call it microservice. Not service, but micro, because we like that term. So it has its own database. We usually used to do that. It's easy to deploy, and it's standalone. Vertical slices. And easy to maintain. How about when it introduces complexity? Because their number grows. What happens when you have cascading effects? If something fails and it's depending on something else, everything will fail. Similar to the monoliths. At least there you knew, okay, it works or it doesn't work. Now you need to find out, okay, the service is down. Then because the other service depends on it, it might be down, and so on. So you have cascading effects. So you needed to monitor them closely, learn a little DevOps, and then the independent units became kind of like this. Yeah, because you didn't analyze, and even if you do, you might end up with something like this. And it happened. Or something like this. So it's hard to manage. So So then you hire a bunch of DevOps to take care of this infrastructure. But, well, do you know that Amazon, for example, I did a short research and services 150 APIs to build a single page? I mean, there's micro as it can in there. Or that Netflix services 5 billion requests a day, and from them, 97 are internal. I mean, we do not see them. Inter-service communication behind the scene. So then you might think, okay, they do it, I can do it. But it's not entirely true, because if these giants do this, not necessarily we can do it in the same manner. So our life will become even harder than with monoliths. So told you that I love them. Okay, so let's talk about HTTP and the synchronous HTTP calls. You basically have an API that issues a request to another API behind the scene. That API processes the request and gets the answer back. Easy as that, right? I mean, it's HTTP, as basic as it can get, and you're happy when this happens. But how about when the response doesn't come back? You're not that happy. And not even so, but in some cases, you might not even know that that request has ever been made. I mean, you issue the request, but on the other side, you don't receive it. So it's like, I don't know, firing something into thin air. You don't know. So I have a short video that calls an I that increases in number. I hope it's visible from behind because it's the only video I get for the streaming. Wait a bit. So in here, come on. It appears like I'm doing something, but I'm not. What? Come on. Give it a bit.
Oh,
Moves?
technical hitch.
Okay, so in here, one request took 20 millisecond time span. What's happening? Okay, anyways. From the one side, if you can issue, 1,000 requests to another API, and in the second API, you might not even get it. But if you switch the context, you made those requests. On the other side, nobody received them. Okay, how reliable is your architecture? So we need to talk about these NFRs. Even as a simple developer, we need to talk about availability. You have two services that uses each other. How do you address availability? If one is down, the other will cascade and fail, right? So how about retries? How you deal with that? We need to implement something yourself to deal with retries. And from the retries part, circuit breakers. Can you tell me anything? Some other patterns that you need to implement and take care of those. Latency. Have you ever worried about network latency? In Romania, we have very high-speed internet, and we don't worry about that. But we usually do application from other clients. So it's not in-house development application that we use in our homes. So how about timeouts? How do you address those? Do you even think about timeouts? Or how reliable is your architecture and your network? You don't know, and you do not even think about it. How about resilience? Does your application are resilient? You don't know because you don't think of those. So some might say, okay, it's perfectly fine to use HTTP between services. And it is, at first. But then, how about all the things we talked about? Timeouts, availability. Are you going back to coupling? Because you basically do HTTP calls, but how do you expose those clients in your APIs? By coupling code, right? Nugget packages with HTTP clients that are imported as a reference in other APIs, right? And you're coupling things. So you can lose requests, and that is not cool for anyone. Retries. Okay, sync, clear. Not cool, you don't know about them. How about async? You distribute load when you do async calls in appearance, because it seems like you issue a request, the response might come back, but it's a might, not for sure. And you have exactly the same issues as in sync HTTP calls. And you can serve more requests. Is it true? Using a sync, you can serve more requests?
Maybe.
Maybe. I hope this works. For example, it's an I that is increased and pushed. 20 milliseconds time span. Let's see how many of them we can push. We wait. 20 seconds, not milliseconds. Cool. That number, big number. What if I told you that the API that should receive this is not up and running? It's not. So using async doesn't solve the problems. Moving on. So HTTP as a protocol is sync by nature. We try to wing it by using async, but basically you kind of make a new HTTP TCP connection for each request. You do 1,000 of them, 1,000 of new TCP connection for each request. You have no retry out of the box and no delivery guarantees whatsoever. Location transparency. If we talk about that, we need to know for sure the exact URL you are calling. And it's good for public-facing APIs, right? You expose an API, a client will connect to that API, issue requests, and it's familiar. So every developer, junior or not, should be able to use this. And it's easy to debug, just because it's familiar. Challenges. How do you do service discovery with HTTP? Out of the box. You need to have a mechanism where to code each and every API, and then in other API, all the URLs that are used in that API, and so on. Not cool. A mess in JSON, usually. Routing, tracing. You will need to have a correlation ID, right? Between each service to be able to trace the requests. And then we settled that HTTP is not cool. We moved to gRPC, but we're gonna skip through this because Steve there has a very good talk on this, so he just might talk to you about gRPC in depth. So basically, it's contract-based. You need to have no-code references, no NuGet packages to share between your APIs. It uses HTTP 2 that it's inherently faster than HTTP 1. And it uses an efficient protobuf serialization that is way more faster than whatever JSON we are using currently. And it's available in many languages. So basically what you have with gRPC is something like this, a specification, where you specify what is the syntax, what is the package, and you specify your service. Basically, it's like an interface in C#. You say, okay, my service needs to have this, and it uses this message format, and you will be able to share this file between different services, and then you'll be able to call these different services without adding a reference in code, which means a little bit more decoupling than in a classical way. Okay, RPCs through message brokers, remote procedure call. So basically it's a kind of API call that is done through something, and that something it's a queue. It preserves encapsulations in systems. You don't need to share code, but it kind of ties the systems together and makes external calls look local. I mean, it's done like this. So we have a service and handler, or another API in our case. We issue a request through a queue, and from that queue, it will be picked up in the handler or in the other service, and the response will get back through the same queue. So pretty much introducing another layer in your application. Fingers crossed. So on the left-hand side, I'm computing Fibonacci, right? So I'm issuing a request to the other side to get back a response. Everything is done through that queue using RPCs through a message broker. So it's pretty much compute intensive, right? Fibonacci for a certain number, it takes a lot of time in a 20-second time span. Come on. So, no. Jesus.
Skip
No. Leave it. So, what I'm gonna show you, it's a RabbitMQ. It's an interface where you are able to see everything that happens through that message queue. I chose RabbitMQ because it was the first system I ever used. But if you switch to cloud, either AWS or Azure, pretty much all the principles apply. So you have queues, and you see your requests in there. What do you gain using this message brokers? So basically, you don't lose the requests. You will make sure that everything you requested stays there, even if it's not processed on the other side. So you'll get reliability, right? And pretty much you don't need to have both systems up at the same time. So whenever the second service will came back to life, if it's dead, it will process those requests and you won't lose them. And you will know that those requests were made. If you want to process faster, you can only add more instances to handle those requests. And then you'll get into other issues, but that's a topic for another discussion. And you can apparently spread the load. Adding 2 consumers or 2 instances of the service that consumes the requests will apparently spread the load, and you'll be able to serve them faster. So you'll get basically an increased throughput. And you will need to match the request with the response. It's still sync because you're waiting in a way from something to be processed on the other side. And then, as an alternative, you go to messaging. Whoever uses a message broker of any kind. Okay? So basically a message is like an HTTP request as its format. It has a body and it has a header, and where you can put different properties to be able to, discern that message. You can add your own properties, just like an HTTP request, and in body it can be pretty much anything. Okay? So messaging gives you loosely coupled integration. You have a system that takes care of your integration points. Doesn't require both systems to be up, and you can do more with your messages. Okay, let's do a request in HTTP becomes a message in messaging. So you can enrich those. You can create pipelines of these kind of queues to enrich the messages or to extract from them whatever you need. So messaging system always trade consistency for availability. About consistency, you will need to take that and take care of it yourself. Involves a producer and a consumer, and it's a term that request response in a way, or handlers. Fingers crossed again. So what's happened, I'm pushing the same I that increases in a 20 seconds time span to a certain queue through a message broker, RabbitMQ in this case. So 20 seconds time span. We have 3,800 and something requests away, and you can see them there because nothing processed them. So I didn't lose them, and the throughput increased like 10 times, which is very awesome. So async message processing, how is this done, or should be done? A request through a queue, a handler, as many as I can push there. A handler will pick up the request whenever the system will be available, so I don't need both systems to be up at the same time, and will push the responses in another queue. And from there, only thing I need to do is to pick them. So basically creating pipelines out of these standard requests. So this is all the fuss about async message processing as a general overview, because deep down there are a lot of patterns. You need to deduct messages depending on your types of applications that you have. And when you have these kind of applications, and you go for increased load and increased throughput, you'll move the problem somewhere else. And that problem will become the storage and the database in our case. Because, why? Let's say we want to process as many messages as we can and to store them in a database. What do you think it will happen? Louder? Yeah. Or you'll get in trouble because you move the potential problem somewhere else. The database connection pool is scarce, and you'll need to take care of those connections yourself and to be very thorough in that. 3,000 requests saved at the same time in the same database will cause you trouble. So it's kind of a reaction to problems of distributed systems. Nowadays, the modern applications require more data, more processing. Their response time needs to be smaller, as small as we can obtain it. So messaging is an answer to that. And then database is a problem. So eventual consistency, it's another topic, but it will be a problem in here if you have such a system that needs to have eventual consistency. How do you solve the database issue? Well, you can batch process the messages. Take them, batches, save them, and then take out another batch and save them. Or can use a semaphore. There are many ways that you can solve this problem, but be sure that it will come up. So why use a messaging system with a microservice architecture and not HTTP? Because you will get faster development. Okay, it's a steep learning curve if you never used a messaging system, but once you get used to it, all the know-how that you'll get, you will be applicable to absolutely any message broker. No integration process. You don't need to create nugget packages. You don't need to, thorough test that. And you depend only on the response. So teams have full ownership. If you have a team that will take, messages from a queue, process them and do something with them, then that team will have full ownership on it. You will not have two teams that will need to integrate with each other, talk, have meetings. Oh, what do you have? What is in your client? What do I get when I'm calling your client? What's in the nugget package, and so on. So it's in a way increases speed of development. Another thing that is very important, you can switch technologies. If you have an HTTP client to another calls to another API, and then you decide suddenly to go from .NET to Go or to Java. I don't know why would you do that, but it can be a scenario. It will allow you to switch to absolutely any kind of language or technology you need to solve your business needs. So you'll be allowed to have a polyglot environment by using this as an integration. Scalability. Okay, we talked in monoliths that we can give a bigger machine. and more machines, and we can scale out, right? And also, from some of them, we can add more CPU or more RAM if we need. In monoliths, we had nothing else to do than to put the entire block and scale the entire block. Now we can scale it in parts, scaling only the parts that are needed. I don't know if the login isn't used that much, but you have an API that processes intensively something, then it makes sense to scale up or out only that part without the login, right? So another thing will be increased throughput. The numbers talk for themselves. Elasticity. You'll be able to scale down and scale up, add more consumers, or add more producers, exactly like in the cloud. Scale up, scale down, depending on your needs, and not only on your needs in terms of application, on the usage of the application. If you have an online store and have Black Friday or Blue Monday, then it makes sense to scale only then. And then you just spin up other instances. And a lot of LEDs we are solving. Reliability, you don't have that with HTTP. Flexibility, you'll be able to have a polyglot environment many of the times. Distribution, increased throughput, I think is one of the most important things in here. Scalability with less money, and performance. I mean, fault tolerance. Those systems handle themselves, right? What tools and frameworks can you use? Plenty of them, pretty much, and many more. There are others for sure. Just a few of them named in here, but all of them function on the same principles. Okay, messaging system, but what are those? Queues are the simple way. We learned about queues in schools, pretty much. First in, first out. Actor model and message brokers as systems. 3 big categories. How does a queue look like? Pretty much like this. You have a sender or an API that issues a request, and you have a receiver, and every message or / request goes through that queue, and it's picked up from there. It's useful for point-to-point communication, so pretty much one-to-one. Messages are ordered and timestamped, depending on the system. You can use something externally, or you can implement it yourself in memory. Whatever suits you best, you can do it. And the preferred mode of picking up those messages from there is pull. So the handler will just get something from the queue. Actor model are born from reactive programming, and I think it's very interesting as a topic and worth exploring. Actor are processes that encapsulate behavior and handle concurrency very well. Can supervise and kill children, and it has at most once delivery. It's born from the reactive manifesto. Pretty much I consider the reactive manifesto the Bible of the modern applications, because an application needs to be responsive, resilient, and elastic, and message driven. So pretty much the modern web today that we all kind of want to code should be, in a way, reactive. So it should be self-contained, should be resilient, should be isolated, should be able to be scaled and react to workload changes by itself without me intervening manually in there. So message brokers are like control towers that take care of everything. Once something sends a message to a queue, one or many consumers will pick the messages from there. It handles very, very well the connections and disconnections from the systems. And it has a concept of dead letter queue, meaning that the messages or the requests that are not suited for processing will be there. You're not going to lose them. You have 3 times of message guarantees. at least once, at most once, and exactly once, depending on the system you are using. And actually, different protocols, not only HTTP, or we're gonna see AMQP. Examples, right, of message brokers. Guarantees and RabbitMQ, because it's super lightweight, you can install it, it has a visual interface that's pretty cool to use, and you can add manually messages in there to test how the application will work. Queues are first in, first out, and it supports AMQP protocol. Come on. What is AMQP? Have you heard about this? Okay. So it's a protocol using communication, born from telecom, if I remember well, and it's async by nature, unlike HTTP. It has guaranteed message delivery, and it has the 3 types of message deliveries, and it's very fast from many points of view. But one of these are that there is no DNS resolve as it is in HTTP connection. And for example, once you open a AMQP connection, you'll be able to pass messages back and forth through the same connection. No additional TCP connection will be made. No DNS resolve to find out that DNS for that API that calls. So, it also has a programmatic routing, if you ever need that. And retries are out of the box. So message will be put back in the queue to be processed further. And you have acknowledge, not acknowledge out of the box. So you'll be able to say, okay, this message is okay, I processed it, acknowledge it, and remove it from queue. And it has the channel concept. It's the same thing that I've told you about. It's like having a wire with multiple wires in front that helps you with traveling the information. And pretty much looks like that. Yeah, concept of the channel. How can you route messages? It supports patterns. For example, if you have logs, you can assign a severity to those logs. And you can send them to different queues to have different people respond to them, or different systems, depending on the severity of them. So this is direct exchange. So you push a message directly to a consumer in a direct point-to-point. You can also broadcast or fan out to several queues and then let consumers decide if that message is suitable for them to be processed. And also you have the topic exchange. This is also found in Azure under different names. So the concept that is the same and the provider is different. So for example, you have patterns. I need to have a message that it has something in front and orange and something else. And then that message will be sent to a certain queue. It's your job to process those messages correctly at the end of the queue and to pull them from there. 2 books as a reference. Very interesting, Enterprise Integration Patterns and Designing Data-Intensive Applications. If you're ever in need to go in depth for this kind of integrations, there are a lot of very interesting things in there worth learning. So what I want you to retain from all my yada yada today is that distributed systems are all about trade-offs. And you need to make a decision, a very informed decision, in fact. If you started with microservices and you went with HTTP, fine with that. But revise your architecture and move it to the next level by switching to, I don't know, maybe first to gRPC. Maybe then to RPC through queues. Maybe then to messaging. Because only then you'll have a reliable architecture that will be suited for many years and alive for many years from now. Take into account, even if you're a simple developer, junior developer, take into account all the non-functional requirements of your application. I mean, think about availability and reliability. Think about if you lose requests or not. And then evolve your architecture. So it's hard when you first start with microservices to pick from all the pool of technologies and everything, but start step by step and then evolve. So only then you'll have an architecture that is strong. Okay, so I think this is it. Just keep in mind that HTTP is not the only option. It's the first go-to option, but it's not the only one. So thank you, and I am gonna leave I'm gonna stay here and leave my colleague there come here. Thank you. Also, if there are any questions, I'm right here.
You show that the messaging is a single point of failure, because if that goes down, your entire business stops.
Yeah, but depending on the system you use, it will have clusters, and it will be able to replicate itself. And if you're in cloud, for example, lucky enough to be in cloud, then that system won't fail. So
Bold claim, won't fail.
yeah. For example, I use RabbitMQ on premise, and we had a guy that knew how to maintain it. So we had a master and 2 slaves, and they were processing financial stuff, and never had an issue with it. So very cool.
Any other questions? Everyone's packed with knowledge. I think we'll take a short 10-minute break. Everyone can refresh their beers, drinks and stuff, whatever snacks are left. So we'll reconvene at about 7:30. That's good. I have a couple of bathroom tokens for those that want.
Cool.
There's too many things.
Yeah, thank you. That's excellent.
Nothing beats the germ exchange, right?
Cool. Hopefully good to go.
Alrighty. You're online?
Yep. I can see us.
Hello everyone. I'm gonna be talking about async demystified today, and I have been given by a Toastmaster one advice: never apologize. So I'm gonna start with apology. I'm freshly jet lagged, so I need my notes. So you will see this weird thing, clicking and like moving my notes over here, so that I don't talk total nonsense. Just a heads up. Anyway, what I want to talk about today is some history of async, how it was, patterns, how they were created in .NET, and the evolution of task and async await. I am actually not super expert on that stuff, but I was extremely interested in that, and internally I poked at people who should be experts, and everyone like, yeah, I know only a little bit. So I kind of got everyone together, including Stephen Taub, and he gave us this awesome talk, and everyone was like, oh my gosh, now I finally understand that, including me. So I said, like, that's what I need to start sharing. So this is ripoff of, with his permission, Stephen Taub's talk internal, but it helped me a lot to understand, so hopefully it's going to understand you as well. We're going to start with ancient times. APM, Asynchronous Programming Model, dates to .NET Framework 1.0, 1.1, 2002, 2003, so a long time ago. And it started with some kind of interface which had basically four things. Is completed synchronously, it had some async state, and it had async wait handle, which was either manual reset event or auto reset event. This thing across BCL, you will find, how we will recognize it. It's something like, begin foo and end foo. It's across BCL. You get the callback state as as an input. You're gonna get the interface which you're supposed to pass to the end. So fairly simple, or when you're used to that. Let's look at how it actually looked inside. First, if you would do the same method synchronously, you would just have method foo. And oftentimes, actually, in BCL, you have that, like either send async or begin send and end send, or just send, which is the synchronous version of that on sockets, for example, or maybe even HTTP, not HTTP client, but something like that. So how would you write the same thing using these begin and end methods? Fairly simple. We would call end foo on top of the result of the begin foo, and you don't care about callback state. You just pass nulls. Great. Now, how would you? That would really create the synchronous stuff, and that's not what you want. How would you use it for the asynchronous stuff? You would call the begin foo, and inside you would do some method that inside. Basically you pass the callback that inside calls the end IAR, and then does some stuff. Again, fairly simple for simple cases. So let's look how it would look like on real cases. Real cases, let's say you want to copy stream to stream. Kind of normal, something comes from network, disk, memory, you have to pass it around, maybe, compress or something on top of that. But, shuffling things between streams is quite, common. So we will have a, while loop, which kind of reads from a, input into a buffer. And whenever it reads into the buffer, it checks out how many bytes, and that sends over to some output. So just kind of pass through. Again, fairly simple. So let's look how the code would look like with the asynchronous stuff. You would call the begin read. That's the first thing. You read from the input. As I said, in the callback, the first thing you need to do is kind of like, hey, I got a callback, which means it's done. Let's end the read. Once you have end the read, now you know how many bytes you've read. So what you're going to do with that? You're going to asynchronously write it out. So you're going to begin write. Again, another callback in there. You're going to find out how many bytes you've written. What are you going to do until after the first write? Well, you should continue to the read. And what do you do at the end of read? Like you do write and again and again and again. And that kind of doesn't scale, right? You would have to actually know upfront how many times actually you need to go deep, which obviously you don't know. So the trick is that this has to be done actually in a loop. And doing it in a loop is extremely tricky. Did anyone did that ever? I did not. I've been told that it's extremely tricky and you shall not touch it. You shall not try. So I didn't. And on top of that, to make things more complicated, this is just the asynchronous path. Like imagine that you want as well the synchronous path, because that's the thing. Like, for example, if you're working with memory streams or something like that, things are fast, or something is buffered. You read 10,000, 10 kilobytes, and you read them byte by byte, or you read them kilobyte by kilobyte, and you read 100K or whatever. Like, imagine some numbers. You don't want always kind of go through the asynchronous path. Sometimes the stuff is already available. And for that, you would have to check the is completed synchronously, and that would make things even more complicated. So how would it look like? In the begin read, the first thing you would start is like, you're going to do the callback only if it did not complete synchronously. And once you call the begin read, if it actually completed synchronously, that's when you do the sum stuff. And you would have to have like very similar path actually in each of those things. Now imagine that in a loop that is already complicated, stay away. Extremely complicated in loops, and basically what people found out that like forget async is let's just queue it on the thread pool. Thread pool knows how to deal with stuff, right? And it's easier to easier to maintain, easy to understand. And as we all know, and I'm a big proponent of like complexity in code, like even if there's benefit, like it has to, you have to pay for that, like because it's hard to maintain. You change jobs or somebody comes along. They have to understand that, or God forbid you move to another team and then somebody says like, hey, this code you remember you owned like 10 years ago, happened to me a couple of times. You don't want to be in those situations. Now, what's even worse is actually imagine that it was the memory stream that I said, and you have this this loop, and it has the is synchronous path. And with the memory stream, let's say the extreme example, it buffers 10K, and you read one byte from whatever reason, like some kind of parser of JSON or whatever complicated language, right? What will happen that actually inside you're gonna kind of call yourself. So 10,000 times you're gonna have the same thing on the call stack, and that's gonna do what? Stack Overflow. There goes the interview question, by the way. Surprisingly, lots of people don't realize that. It's like, yeah, here's the DFS or the recursive algorithm. Like, done. Like, okay, what's the problem? Recursion is bad. So those things kind of led to something that this was not ideal. In BCL, it's used a lot because you've seen lots of the begin and end things. You see knots, heavy knots over here. Somebody has lots of experience, I'm sorry. And if you look actually at the code of the BCL inside, you will notice that we have various wrappers around these things to make it simplified and specialized for something called lazy async result, and very complicated overall. So no fun at all. So what we did in .NET Framework 2.0, this is not .NET Core, this is .NET Framework, so we're still talking ancient, like 2005-3, I believe. And what we introduced is the event-based asynchronous pattern, which is awesome because it has events, it has sender, event arguments. Turns out that it didn't solve the problems with the loops. It was interesting idea. Apparently we found out after shipping right away that that doesn't solve the main problem that we had with the previous system, but we had a new thing. The interesting thing that along the way we actually, for this thing, we actually introduced execution context, which is something that survives to today and is important. I'm not gonna touch on that, but it was not entirely lost cause, except that we invented something that then we didn't find really useful. And I think it's used about like 5 to 10 classes in BCL, like SMTP mail and TCP client, background worker, and a couple of other things. Even in core probably. Hopefully we will rewrite those things eventually. So that's actually a great example of like sometimes it's good to validate what you're trying to solve before you ship something. It's kind of natural. One would think that everyone does that. Well, sometimes not. Such is life. So we're gonna get to task. That was the magical thing in .NET Framework 4.0. And interestingly, it started as a MSR project. So MSR is Microsoft Research. It was around parallel computing, and that was basically just divide and conquer efficiency. So think quicksort, like I have part that I need to do here, over here, just like parallelize it in 2 threads, like go parallel and then maybe merge sort or whatever, do with the results. And that thing, so it was like heavily computing. It was nothing, about like general asynchronous or anything like that. But it shaped the task, and actually it's similar to today. Except that Stephen put it nicely, that like the 90% of task is right, and 10% still keeps him up awake at night sometimes. And he would love to get rid of it, but because compatibility is king and we shipped it, we're never gonna get rid of that. And yeah, that's sad. It's sad. But anyway, so it's mostly right. So what does task do? Or it represents basically general work. It can be compute, it can be IO bound, it could be anything. It's under terminologies used promise, future, or whatever from other languages. And basically, it's the key thing to understand, and that people have hump, and we didn't help quite, them with understanding, is that it's not tied to thread pool. The task has nothing to do with thread pool. And it's not tied to executing the delegate, because usually, like if you've seen, you have the begin foo, and then you pass the delegate like, hey, once you're done, call this. At least on creation, the task is not tied to that. Now, what you can do with task, you can like shove some results into it. It can be completed, and you can wake up somebody that's waiting on it. So somebody can wait, which is good. And we have two parts: task, which is task of void, kind of, right? And task of T, which is the generic version, when you have the optional result T, for example. We have seen, like, synchronously read me some data, how many bytes you read, right? That's kind of useful information. So these type of things. So what we have inside the task or task of T, we have the T, only guys, task of T. We have some state related to synchronization, and we have actually some state related to the callback, even though I said it's not responsible for the callback. Actually, we store some stuff, but we don't store it upon creation, which is the big difference from the previous patterns, as we're gonna see. With task, there's maybe a little bit less known concept, task completion source. Actually, who knows what task completion source is? 2 people, 3 people maybe, or 4 if I back. Okay, out of 30. Let's find out what it is. I'm gonna move my notes so that I'm not talking nonsense entirely. So task, I'm gonna first describe task. Task is something that, you come to it and you say like, here's a callback, invoke it when you're done, or if you're already done, just, or right now. Well, invoke it right now if it's already completed or if you're done, right? So it's kind of pass through, like, you can hook up something. You can hook up multiple things, by the way, which is pretty cool. Another thing you can say on that, like, hey, I want to wait here until you're done, right? So you can kind of block on it and just wait, you as a user. The interesting thing that it cannot be completed by user directly. So if I give you a task and you see lots of APIs giving task, it's like you can consume it, you can hook up to it, you can wait on it, but that's it. Like, you cannot say like, oh, and you're done. And that's actually is the role of the task completion source, which is basically a wrapper of task. Internally, it has the kind of field of task inside. And it's sneaky. It uses internal methods because it's in the same assembly, right? Internal methods to actually set result, set exception, and set cancel on the task itself. But nobody else except task completion source can actually mess up with that. Which means you, as somebody, if you would kind of create these things, and we're gonna get to that, you are in charge of, like, if you want somebody else except you to as well decide when something is done. You usually don't want to do that, but if you want to, you have to pass along the task completion source. If you just like, hey, I just want to pass it along, people can hook up to it, wait on it, or whatever, kind of wait for the result, look at the result, that's when you kind of deal with task, which is majority of the cases. So, move on. How do we consume task? Let's actually look at an example. So if you have task of T, you can either call T.wait, which is basically the blocking part, as I said, like, hey, wake me up when you're done, which, if it's already done, it's not gonna block at all, obviously. Or you can call T.continue.wait and pass it callback. Which is basically you come along and say like, hey, when you're done, or if it's right now, like, this is what you should call. You can actually have multiple those, callbacks. So you or multiple sources can actually hook up their own callbacks. The order is not guaranteed, and and it's always asynchronous. There's kind of option to override that, but that's not, the major thing. Later we will see that the principal difference is, like, when you look at the original stuff with the begin foo and end foo with the APM, it's not that different. Callbacks were there as well, except the callbacks were there at creation. The beauty of the task is that, and that kind of messed up things, because at the creation you already have to know what you're gonna do later. Over here with task, you basically say, like, this is some work, pass it along, and whoever wants can hook up, and they decide what's gonna happen later on in their callbacks. So kind of this separation and not doing it during creation is what gives it flexibility. And that allows actually things like await to get hooked up. And before we go to that, I'm gonna tell you as well the sad story of the task.run, which is, task was beautiful, except that task.run is something that actually is tied to thread pool. And because it takes delegate and it's gonna execute it, it adds a field of the delegate basically during creation kind of thing, and it queues it to the thread pool. So that's the tie. We would love not to have it. The thread grabs it, executes it, marks it as completed, it's done. The interesting thing that it's not that difficult to kind of implement that, yet it's handy, so we put it on task, and we're sorry. It should have been like an extension function somewhere hidden, but anyway. This is how actually it looks like. It's a great example of how the task completion source would look like. So first you would create the task completion source. Then you would say, like, okay, I have something to queue on the thread pool. And inside you would just call the function f that you are supposed to run. You get the result, and you set the result on the task completion source. Simple. Then you're gonna return. What you're gonna return, you should return task. So inside the task completion source, I said that it's just a wrapper, so you would return the task inside. And to be good citizens, we would kind of do some exception handling just in case, which is the set result, set exception, and the last one was set cancelled, which is usually external. External call. So that's not in here. Fairly simple, yet we have a function that confuses everyone, because if they do task.run, suddenly it runs on thread pool. Why the heck it is not tied to thread pool? It is. So async await, that came around later in next version, .NET 4.5, apparently C#5. Great numbers, synchronized. And I'm gonna show you some example of how the asynchronous call code would look like or how does it kind of operate on the async. I'm gonna dig deeper into the async, what's happening inside, and how it looks like. Just gonna need to. So imagine that we have this, and imagine that this is something that goes across the network. So some get data, read from network, put data somewhere else. Like the same way we had it with streams, like read write, something similar. How would we use it? Using just the task as we learned right now. So we would call the get data async. It would give us the task of t. And we would hook up like, hey, where you're done, we need to do something more, copy the data somewhere else. So we would want to put the data and use the result of whatever, from that task actually that we got. And let's say that after that, we want to say like, hey, we're done. So we would hook up another continuation on the second task. Fairly simple, except that, who would want to look at that? So how does this same code would look like with async await? So who is familiar, who used async await in the code? Okay, almost everyone, so let's drop it like otherwise. Who rarely used async await in their code? All right, everyone knows that. Perfect. Even though people are usually not want to say no and raise their hands. So in C#5, this is how it looked like. You would get the task of t, you would await the t, and that would give you the result. Then you would kind of put data, like call it on the result, and await t2, and after that's done, you would write line done. Which is like kind of straightforward, logical. That's how in your head it operates. So that's why kind of the async await is powerful. But actually what it does, behind the scene, it generates exactly this thing, which kind of hooking up the callbacks, except that compiler magic does magic for you. And let's look at actually, the interesting thing is that I'm gonna see that the compiler, while it does magic, it does not recognize task as a specific type. It's basically using awaiter pattern, which in other words is duck typing. This is basically the first time when I finally found out, like, oh my gosh, duck typing is awesome. And in the compiler, it really is. And it's extremely powerful. We're gonna get to that. So the task is not known. What actually the compiler knows is that it's gonna look for certain patterns. Like if you have this method, and if that method returns something that has that method, okay, I'm gonna treat it as a task. So it's kind of some task-like. And whatever is task-like, you can write your own. I would not do that, but you can. You can then kind of hook up the await, and async will automatically kind of light up, which is freaking amazing. So how does the awaiter pattern look like? Let's look at the int a result await t. It's translated into something that on t, which is the task or task-like, compiler is gonna call get awaiter. Then it's gonna expect that whatever is returned has something boolean, is completed. If it's completed, it's gonna do something complicated, and eventually, if it's not completed, it's gonna do something complicated. We're gonna look at that later. And if once it's completed, you're gonna call on the awaiter get result. So these bold methods are the only three things that actually compiler looks for. If you kind of create my task fun with these properties, it's gonna light up, and then you have to put some magical, I believe, attributes for kind of other things. But this is basically it in a nutshell. So how does it look in details? Because it was kind of simplified version. You're gonna see this now on a few more slides as we're gonna go deeper. In fact, it's actually part of a method that's kind of called move next, I believe, everywhere, and it's basically state machine. So it is some kind of, hey, if state 0, go to label 0. This is probably the only place that you're allowed to use go to. Otherwise, please stay away. If you're coming from C++ like me, stay away from go to. It's evil. It's evil in even C++. In the not is completed, what we're gonna do? We're gonna say, hey, okay, we're here. It's not completed. Let's say it's state 42 because that's the answer to everything. And on awaiter, we're gonna say, like, hey, uncompleted, call move next, which means we're gonna register ourselves. Come back, call me back one, dear awaiter, when you're done, and then you're gonna return. And over here, early on, we're gonna say, like, hey, if we come back to the move next, if we're in the state 42, guess where we're gonna continue after the not is completed on the 42. And basically this state is generated for every await in your method. So you have multiple awaits in your method. There's a state machine. This is part of a structure which we're gonna soon see. I can't even speak. Which we're gonna soon see, and part of that is this method, and magically everything is there. I don't know what I want to say. Anyway, move on. State machine. Let's look at the state machine. Let's imagine another kind of counterexample and motivation for why it's more complicated. This is your method, foo, whatever. First you read lines, something from user, some input from somewhere. Then you await something, and then you're gonna say, hey, we're done, including the input that you got from somewhere. As you have seen, the await basically does the continuation, so it comes back, and the question is, like, so how does the method actually get to the X, to the read line, to the input? It's fairly straightforward. There's a state machine. This is the structure I said, the method foo state machine, where we have the move next method, which we have just seen, and inside we have stored locals of the method. We have parameters, so the X would be there as a local, and we have the awaiter and we have the state. In a nutshell, those are the things which are there. Let me check my notes if I don't miss anything important. Oh yeah. I did over here. So how does the X survive? Like, as I said, it's basically, this is the capture. Lambda functions do that as well. They do the capture, magic happens, and basically they take out stack-based variables onto the heap, because this can potentially live on the heap, or even if it doesn't live on the heap, like the fact that string is over here, that refers to something on the heap. The other things that actually, compiler is smart. Obviously, it's not gonna store every single local. It's just gonna look like whatever is really used across the boundaries of the await. So that's good. You can trust it. Interestingly, that this is structure. It's actually because of performance. We're gonna talk about it more in debug version. If you compile debug, this is gonna be class. Why? Because of debuggability. If these things are around, if you kind of escape thing, taking out like local structures on your call stack, good luck with that. Optimize debugging, fun. So in debug, it's kind of creating classes, but each class has to be basically per call. This is instantiated per call, has to be allocated on heap, so that's a burden, something we want to avoid. Example would be again like if you imagine that you have buffered stream behind that. Again, you read 10,000 bytes and you're reading one by byte. In each call, we're gonna allocate this struct. Like if it's the struct, it's on the stack. Cool, nothing happens. If it would be class, it would kind of suck. So we're gonna look at example a little bit more deep dive how these things look like. We're gonna translate this simple function that basically what it does, it awaits delay. So it's kind of fancy delay, right? But what's gonna happen inside? First of all, we're gonna have the state machine. So we're gonna store the timeout because it's a parameter. There's no locals, so if there will be locals, they will be there as well. We're gonna have the move next, which we're gonna dig deeper into later. We're gonna have the state, and we're gonna have the later. What will compiler generate for the function? So it's gonna create basically a similar function, except that it's missing the async. That's kind of compiler goo. You can use await. Over here, we're not gonna use await. We're gonna have already translated thing that compiler generates. So first thing, we're gonna create the full structure. This is gonna be on the stack. If it would be class, it would be on heap, and that's exactly where per call, as you will see, we would kind of get the allocations. We're gonna store save into the structure the parameter. We're gonna initialize the state, and we're gonna call move next. And then we're gonna return something. And the return something is a little bit, more involved, and we're gonna look into that in the next slide. So, same thing, didn't change anything, except like shifted a little bit, same code as before, same state machine. So what's gonna be there next? In the move next, the key thing is that we're gonna have to have as well the task completion source or something like that, because the same way I said that task doesn't have to be task, it's task-like, and that's why we have the awaiter. The task completion source in principle is not itself, but something like that. But anyway, let's call it for simplicity TCS or task completion source. And in the move next, eventually, when we're gonna get to the result, we're gonna set the result. Somebody has to allocate the task completion source, so that's gonna be over here. Before you call the move next, and when you're done, we can actually go into the task completion source and return the inner task, which is what we're supposed to return. So this is how it's gonna look like. Now, what's the problem here? There are a couple of problems. Problem number one, there are two allocations per each call. So the full stack machine, that's struct, that's fine, But over here, task completion source, that's an allocation on the heap, and inside is task itself of task. So that's another allocation, two allocations, and that's kind of per call. It's a little bit bad. It's it's a little bit too much. So what we invented a little bit later on, .NET Core 2.0 or something like that, and actually we didn't backport it, but we made it extensible through the duck typing actually to .NET framework as well, was value task. And value task, or not only value task, but the value task, to enable value task, we had to create that instead of really newing the task completion source, what we really do, what the compiler does, it searches for special custom attributes in all your classes. And one of the classes, in this case, async value task method builder, not in this case, but if it would be for value task, says like, hey, I'm the builder for that class. So compiler knows that instead of doing new task completion source, because it doesn't know anything about that, knows that, hey, if I see this type, I should instead do this builder dot create. And the dot create magically, if it would be this way, it can just new up on the heap, or it can return a struct. If it's a struct, it stays over here. Beautiful. We avoided the allocation, everything stays on the stack, just copy bits in memory. So we got rid of one allocation. How do we get rid of the second one? That's actually more complicated. And obviously this would have to be replaced by the not task completion source, but the builder And basically the builder pattern, again, duck typing would be that it has to have create and task, dot task, and probably a couple of more to make it really work. So what about the task allocation? So the builder can reuse the known tasks. It can, for example, reuse completed task if you don't have any value. Hey, I'm done. If it's Boolean, task of T, task of Boolean, you can say like, hey, I have actually two. I have true or false. So what if I create them, cache them for the entire process, and whenever somebody asks, I return them. Yeah, if you hook up with that, it's gonna work. For int, we have actually, interestingly, we cache 9 of them, or actually 10 of them, from -1 to 8. I'm not sure why, but that's, somebody somewhere figure out that that's a smart thing to do. Other thing that you can actually, the builder can do, it can kind of look at the last completed. So imagine that when you're copying the buffers between streams, usually you read, for example, by 1 kilobyte, 4 kilobytes, whatever, same size, and at the end it's suddenly smaller, usually, either 0 or something, in between. So you can basically reuse the same task for all of them except the last. That's a huge value. For example, on SSL stream, all right. I've been told that I'm talking too long or something. On SSL stream, it doesn't work. SSL stream is like SSL, where you basically have you encrypt headers and then you encrypt HTTP body. HTTP client's coming back, and the size of those alternates. However, you could be smart and maybe create, like if you get typical same things, you could maybe cache 2 of them or play some games. Anyway, starting getting a little bit complicated. On top of that, the size of the task is 64 bytes or 72 bytes, which, if you look at the Azure workloads, it's fine because it's going to get GC collected, some kind of Gen 0 eventually will kick in and stuff is okay. But if it's hot path, for example, you're really kind of sending on sockets like there and back, something really, really fast, it can show up to 5-10% degrade of performance because of the GCs, because here and there GC will kick in, it's going to delay stuff. So what are we going to do about that? We could give up, but we know better, right? We love performance. I need the next one. So that's why we invented the value task. It came in .NET Core 2, and as I said, also NuGet package. And it's one of those things that is task-like. So it has all the beautiful things. So all the work we did, like how we abstracted the compiler to not hardcore the task, kind of paid off with the value task immediately. And inside the value task, you have 2 options. You either have the value T, which means if you end up synchronously, you immediately hold the value, or if not, then you have the task of T. And all the functions of the value task basically look like, only one of them can be kind of value. Either it's default and some value, or it's some value and then now for the task of T. And all the methods look like, hey, if the task of T is now, okay, we have results, use the results, otherwise do something else. So if else, very simple inline methods. Now, the funny part was, value task is awesome because it's a struct, that's the key thing. So it stays, for the synchronous code path, basically, you avoid the allocation of the task as well. So we were trying to get rid of 2 allocations. One was the task completion source, and one was inside the task. So the task completion source we did by having the builder, which can return struct, and this is the value task instead of task. Now the trouble is that we couldn't just go and override on return value because C# doesn't know how to do that. Luckily, in .NET Core 2.1, we invented something like memory of T and span of T. You probably heard about that. And that required new overloads. And we said like, when we're adding new overloads and memory of T is usually around performance, let's use the smart thing. So that's actually interesting that sometimes in code reviews, you will see comments that like, yeah, you're passing this array here, but can you please do like new memory of byte over the array? And people are like, why? That's useless. Like, no, that's gonna call the right overload later on and like avoid the allocation down there. So there's sometimes kind of these tricky things that you can see in the code base. And again, I'm talking about code base which is focused on high performance. It's not about something that you would write in, you should use kind of as a pattern, in general. In general, we can actually, the part of the value task is like, what do we do about, in average, the 1% of asynchronous case? So mostly you end up 99% synchronously. Good, we have it. no allocations. But in the 1% case, we have to allocate. So in .NET Core 2.1, we added one more thing in the value task. It's the iValue task source, which actually which is very similar to to the awaiter pattern. So it has as well, like, are you completed? You can hook up a callback to that and get a result. And it made all the inline methods, instead of binary, like, if this is null, then that, it just makes them trinary, like so, because only one of these things can be non-null or non-default. So fairly simple, except that it's extremely difficult to kind of get it right. And this is, if you don't have the T, then it's like task versus iValue task source only, without the T. And the key thing in that this interface can actually do whatever it wants, including resetting and reusing stuff. So you can, like, before we, once we pass something, we don't know when it's done. But sometimes you are smarter. And again, you should not try to be smarter. We tried sometimes we pay for it. But sometimes it pays off. For example, on sockets, we have begin and send. And we know that there cannot ever be two sends. So as soon as we kind of call another send, we can reuse the previous one associated with that particular socket. So that's kind of the thing that kind of allows us to kind of reset previous value and that stuff. But it's extremely, it's basically bringing the C++ness and the problems with time, lifetime management, all those things into C#. So that's why I kind of stay away. Except that when you look at that, it's kind of cool. You can use these things and really avoid, inside on the really important high performance code pulses, these allocations. And there are like third-party libraries like Redis and a couple of MVPs are actually hung up on that and use that but again, in the cases where the complexity really pays off, because the per benefit is huge. So what did we learn today? Summary. See, some are falling asleep. I don't blame you. It's too hot in here. We started with the APM, asynchronous programming model, ancient thing, async result, begin foo and foo. The problem was it was limited nesting, and you had to do loops which were extremely complicated. Eventually, we replaced it with, we invented event-based asynchronous pattern, which did via EM events instead of the begin and end foo, but basically the same problem as the previous thing. It brought in other things as well. Later on, we invented task, which has the wait, which means you can block on it, or continue with, which means say hey, call me when you're done over here, but you hook up the callback post creation, which is the huge difference against the APM. And it has the combo of task completion source, which is the magical thing controlling the task, and which is able to kind of set result, cancel it, throw exception, and that stuff. And that's what you should preciously guard and not give away. On top of the task, we created the async await. You can see that it's always something good is created, and the next release something better is on top of that, which is good. So we created that. It has awaiter pattern, state machine. So async await is not hard coded to task. It has task-like things, duck typing sometimes. And later on, .NET Core 2 that actually enabled us to do the value task, which is you should not use unless you're really on hot path, because it comes with baggage, and some hyper optimizations are possible, but you should not do them. And that's it. Thank you very much. Hopefully you enjoyed. Alrighty. Do you want to do general Q&As?
Yeah.
I warn you, I don't know much more than what I presented. Go on.
Yes, I think it's just a point where I was confused, but you demonstrated the generated code when you write an await, and inside that generated class there was a task, and you mentioned that it was the inner task. I'm just wondering where the source of that inner task is from. Is that the task that you came into the new generated code block with?
So that's a very specific question, which I should report. We are still streaming, right?
Yes.
Yeah. We should. So it was about if certain code where the task came from, which I think probably get to that. But the bottom line is that the task is part of the task completion source, basically over here. That could be it's instead of creating task, you create a task completion source, which is the driver. and then you decide whom then you decide whom to share the task with, because that's the thing that cannot harm others. Because like if your source, for example, let's say you're in charge of reading something from network, you don't want to hand it out and somebody says like comes along like, yeah, you're done. Like, no, I'm not. I know better, right? So you want to have full control. It's basically in that data structure inside as one of the fields.
So that's the owner of the task completion source.
Yes. Sorry. Task is not owner of task completion source. Task completion source is basically owner of the task, but then passes it along, is like, go hook up to it, wait on it, whatever. This is kind of my interface, For the task completion source, I'm the one doing the heavy weight lifting synchronous thingies. Here's the magical thing that you can observe other people. Yeah. We can, by the way, ask questions as well for I think it doesn't have to be deep into this thing. I'm actually scared of deep questions. Anything else?
So you said you got each release before. Is it done now, or is there something?
Oh, the Stephen Top is amazing, like that. And I believe that Ben Adams actually is still parting on that and doing more improvements on that stuff. At MVP Summit, I should catch him and pick his brain to what to add to this talk, but. Again, it's gonna be more craziness. Again, more things which will be dangerous, and the same way, spanner memory. Who heard about spanner memory? Okay, quite a few, almost 3/4. Who used spanner memory? There we go, 4 people, right? And that's how it should be. Right? It's a cool thing, knowing that you can get with performance of some high-level language to the performance of basically bare metal, C++ assembler. But again, when do you need that? When you write your business logic, hell no, stay away, right? That's not the right place. If you're writing library that is kind of hyper performant or whatnot, that's the time when you should use that. Why did I start on this ramble? Sorry, I will blame that I'm jet lagged. If it's continuing, and Ben Adams. Again, it's cool things to learn about, that things are happening, the better performance is coming along and whatnot. But it's not something that people will use in daily lives. On the other hand, it's always cool to know that, you could do cooler things, right? You can play, have a toy, and you could achieve as well in libraries something that is really hyper optimized if you would have the business case or business reason to do that and go into that complexity. Does that answer your question a little bit? Yeah.
I've got one, but it might be an edge case. Configure await. How does that kind of come into this?
It's there. Yes. I don't know, to be honest. I don't remember those details. The key thing that when people ask about configure await is often the true and false default. That the default, I think, is done for applications. So I forgot it's just the false or true, whatever, right? So if you're writing application, that's the right default. If you're writing a library, which most of our MVPs and active people on Twitter are, it's exactly opposite. So they will say why the heck did you set up this this value differently? Another interesting thing with the configure await is that people sometimes ask, so can I change default per this library? And that's, for example, from .NET team, we're like, let's not do that. Now imagine you parachute to any code, you don't know any context. And you have to look at it let me look first at the project file, what's the default, so that I know actually what I'm talking about, right? It just doesn't make sense. So there's no good, from usage perspective, there's no good way to set the default. Either you have this set of people or this set of people. We chose the vocal people and play for the normal people. So yeah, cool. That's what it is. And how it exactly works and that stuff, honestly, I don't know.
Okay.
Yeah. All right, we're done.
Looking good.
Yeah, we can go mingle if you have questions about anything .NET, I bet, or HTTP or whatnot, Romania. I'm not gonna answer those questions here in Avel.
UK.
UK versus England. Steve is my answer on that.
We'll get a map on the screen.
Yeah, we're more than happy to kind of hang out a little bit and talk with you folks. Come on, Steve.
So yeah, big thank you as always for everyone coming along. Good to see a really full house this evening, and some new faces here as well. So that's been great. Thank you very much to Irina and Carol for not only flying from Seattle to London, but then coming down on the train and risking Southern Rail to get here. So
What is that again? Oh, okay.
The train we got.
I'll explain on the way home. If
All
we make it.
right. You put us in danger.
Hopefully see you all at the next meetup. I've got the dates online. I can't remember without a slide to help me when they are, but somewhere in February we have our next meetup about something.
Something cool.
Palumi and F Sharp. That's what it's about. Well done. Right.
And now
to
you
hire you.
And now you'll figure out like how to stream and everything, so it's gonna be even cooler.
I may invest in some additional hardware, and we may do some more streaming. So, but do enjoy it. If there's any snacks and drinks left, do enjoy them on the way out. If you're sitting on a white seat, would you mind? I'll move the stack out the way, and then we can just stack them as we go out. Because I'm leaving this place in disarray for someone to sort out in the morning. So the least work I can give them, the happier they'll be. But otherwise, thank you very much, and see you next time.
Thank you very much.
Awesome. Good talk.
Thank you.
Okay. Yeah.
I had to read the slides
I know
for 30 minutes
some
because
stuff, and I know
forgot
that
the details.
core it doesn't really matter because there's no synchronization context. I've run headfirst into it so many times.
Because of the sort of synchronization context it's got.
It's not that. Most of it's basically, so you're touching limits of my knowledge. I didn't joke.
I don't really know the inside of that, but what it said was in .NET Core, the way they're doing it now, that it's sort of truly parallel when you're doing async. And they gave an example of where you can end up, you can have something like if you were trying to set a value on a collection. In the old .NET, in the .NET framework, if you did a load of async tasks, it was actually underneath, although they're all kind of waiting, they end up, only one thing will hit the collection at a time. Whereas in the new .NET Core way, you can actually end up and causing deadlocks in your code because it's now truly truly asynchronous rather than parallel.
This is the first time I hear anything about like.
Yeah, but it's a Microsoft blog post on it. I just read it the other day and I thought, oh, that's really interesting because the performance has gone up, but the potential for blocking in edge cases is
and that might be one of the things of using exactly the value task and that stuff. Once you want to kind of like hyper optimize for certain cases, then you might kind of bring danger of somewhere else. The good news is that in .NET Core we could start breaking people. Obviously we're not like, let's break people, but when you see like, hey, I can gain quite a lot for maybe breaking some kind of corner case, maybe it's worth it.
Yeah, I think it was safe collection probably solved it.
I have a complicated question.
All right, I'm going to have a very simple answer. I don't know.
Well, I think a kitten might die as well because I'm going to talk about running asynchronous code synchronously. Will I use
sync over async?
Well, I use a testing library called machine specifications, and the way that it works is that you have your arrange, act, and assert, essentially the equivalents, are treated as delegates, and the delegates are basically a void. They're an action.
Okay.
So, in order to make each of your phases run, you need them to run synchronously, which is a pain because it just makes it very difficult. You end up, writing get away to get result at the end of each of your methods. And I was wondering, I've been looking at trying to find ways of determining when I'm past something. I've been trying to use reflection to work out if it's an async method, and then trying to find some way of running that in a some sort of wrapper that then runs it as a task, so that because otherwise what happens is that you're passing a task from one method to from one part to the next. So I think it's probably a fault of the fact that this was written, I think, in 2009.
I understand now. So we're just saying that they have like a bunch of synchronous methods?
The way that it works is that you create a load of classes that have delegates attached, and you have an arrange delegate, an act delegate, and then a bunch of assert delegates.
Okay.
And those basically, you declare them as being an action, essentially.
Okay.
So the problem is that if I write async